Okay.
Good morning, everyone. Welcome to Nano Open Webinar. We have Dr. Albert Heinrich Lanthaler from University of Southampton today. Dr. Albert is one of our TEAM-NANO researchers. He will talk about materials and fabrication methods for sustainable smart textiles. Before Dr. Albert starts his presentation, I would like to give you a brief introduction about him. Dr. Albert Heinrich Lanthaler received his bachelor's in 2019 and his master's degree in 2021, both in mechanical engineering from Università degli Studi di Parma, Italy. In 2022, he was enrolled in the Advanced System Engineering PhD program at the Free University of Bolzano-Bozen, aiming to develop sensors and systems for smart textiles based on recyclable, biocompatible, and biodegradable materials. In November 2025, he started his postdoc at the Flexible Nanoelectronics Group in Southampton, focusing his research on flexible and sustainable nano devices within the TEAM-NANO project. Welcome, Albert. The floor is yours.
Thank you. Thank you so much, Dr., for the very nice introduction. And thank you all for having me today and giving me the possibility to present my work. Let me share my screen. Yes. Can you see my screen? I hope so.
Yes.
Yes. Lovely. Perfect. So let me, sorry. A big spoiler here. Okay, so as mentioned by Nocta, today my presentation focuses on finding a way towards a more sustainable smart textiles. Without any further ado, let me start with a very brief introduction outline, about my today's speech. I promise it's going to be very brief. So I'm going to start giving you a brief introduction about smart textiles and particularly about how to be more sustainable, and a motivation behind such a reason, especially considering nowadays sustainability concerns. Next, I will move towards presenting all the materials and methods I've developed during my PhD and my postdoc at the University of Southampton to fabricate such devices. I will conclude my speech with some outlooks. And of course, I would like to leave you with some very interesting further readings I found in literature. So, I don't know very much about your background, but to give you a very basic idea of what e-textiles are, I would like you to think of a way to integrate in basically nowadays textiles. Let me see if I'm able to pointer option. Yes. I was saying nowadays textiles, so all the textile you can think of, garment, t-shirts, yarns, and so on and so forth, electronics, in many different ways. First thing first, of course, the electronic textile find application in a very broad fields, starting from LEDs, photovoltaics, up to haptics, medicine, and even up to antennas. And also, of course, these sub-applications, let's say, find applications again in more broader fields such as automotive, defense, aerospace, healthcare, and so on and so forth. Before moving on, I would like also to make a distinction between smart textiles, in which basically the textile can act as sensors of external stimuli. The stimulus can have different natures, as electrical, thermal, chemical, magnetic, and so on and so forth. And the sensing element is embedded into the very textiles we are using, so it reacts and adapts to the stimulus itself. Another field of another category, of e-textile is the wearable computers. As you may be aware of, these are data processing systems attached to our body. I think we all know what a smartwatch is, for instance, or a smart goggle. The input data comes from the sensor, and then that coming from the sensor is processed by the units itself, and the output is recorded constantly, no matter the position of the body or the specific task. We have the three-level integration as described by Kunigunde Cerenak in 2012. So the first one, the most basic one, is the conductive yarns and conductive fibers level, in which basically the idea is to replace conductive bulky cables with conductive yarns, but still integrating bulky electronics on the very textile, as this example here showcases. The second level of integration, and specifically the one I was mainly focused on, is based on the idea to use the textiles as sensors or actuator, and at the same time take advantage of some other parts, let's say, to collect and log data to still be in a more bulky way. The third level of integration, of course, is the one we all aiming for, is to have the logic boards and the whole electronic embedded and made out of textiles themselves. As promised, I would like to give you a motivation behind my topic, and I would like to show you first this graph here, which basically reports the expected growth of textile market up to 2030. And although the textile market already is one of the main causes of the pollution of our own environment nowadays, we are expecting a steep growth of the market until 2030. So I would like you now to think about also the impact of the electronic itself market on the way we are polluting our own environment. And imagine to combine these two huge players in such nowadays concern merged together. So even though the majority of the textile introduced into the market are declared not as fully recyclable, the 85% of them are not recycled at all, meaning that around 38,000 tons per year of spare textile are dumped into landfills and pollute our ocean. So how to sort this issue out? Well, my idea is to basically focus on more recyclable and biodegradable material for both electronics and the textiles themselves, to have a better control over chemicals involved in the process. Again, from the very starting point of the textile fabrication up to the electronic integration, so in the clean rooms, for instance. And last but not least, to have a better control and to slow down the consumption of raw material, energy, water, but last but not least, the soil consumption. So during my PhD thesis, but also nowadays during my recent postdoc position, I wanted to focus on the sustainability also of the design of the device itself. How to do that? Well, starting from the very platform, so the textile itself, I would like to focus on more biodegradable and biocompatible material, such as textile made out of hemp, bamboo, nettle, or speaking of biocompatible, polyether cotton, for instance, plays an important role. Coming to the metals themselves, I try to focus myself mainly to more mineral-based metals, such as zinc, for instance, very abundant in our on our planet Earth, or magnesium, manganese. Speaking of green dielectrics, without mentioning, of course, silicon dioxide, aluminum oxide, Parylene C has become very interesting and attractive due to its stability in environment. And of course, finally coming to the green semiconductor. Here I reported two N-type semiconductors. One is indium gallium zinc oxide and the other zinc oxide. They can be easily solved in water, but also other example can be nickel oxide, copper iron oxide, or manganese dioxide. Coming to the electronic fabrication, in my speech, the focus was mainly through the utilization of the sputtering technique. So basically, throughout the activation of a plasma on a metal semiconductor or the electric target, the idea is to detach atoms from the very target and deposit them throughout the activated plasma and a high vacuum chamber on the very target of our interest, in our case, the textile. And the deep coating process. So the idea is to take advantage of the porosity of the textile themselves, either yarn-wise or lattice-wise, to be coated with different materials. Coming to the patterning, since I mentioned before, I wanted to get rid of the majority of the chemicals involved in the process, meaning that all the photoresist and etchants are not well designed in this work. I tried to focus mainly on the shadow masking effect, meaning that we are applying a mask on the very substrate we would like to fabricate on. And basically, you are depositing everywhere the thin film coating via sputtering, and then after removing the mask, as you can see, the desired layer stays on the textile itself. So, to give you an idea of the methods, again, speaking about characterization, I divided into two main fields of characterization. Having a look at the textile properties, for instance, we wanted to achieve flexibility and to check the flexibility of the textile itself before and after the electronic fabrication, taking advantage of this surely bending stiffness tester. It's very nice. The idea is to place a piece of textile over here over the top and push forward in order to bend it, and based on the let's say the total length of the textile until the very moment it touches the bent area of the tester, we are able to throughout mathematical calculus, we are able to determine the stiffness of the textile. The breathability, of course, is another very interesting topic nowadays, because of course we wanted to preserve the breathability of the textile we would like to deposit electronics on. The material absorption, speaking of sustainability and material wastage, nowadays is very much important to understand the total material absorption of the textile we are currently using to cut it down as much as we can, and the recyclability. Possibly what we would like to achieve is something like that. So a device entirely fabricated on a fabric, and then after recyclability cycle, we want to achieve. We want to be able to refabricate on the very same substrate we used before. Coming to the electronic properties, of course, we would like to investigate them as well. Well, I tried to start on a very basic level. So I started fabricating temperature sensors. So of course, it's a matter of characterizing them under different temperature behavior, but also since I was able on the very last work now I'm presenting nowadays to achieve some very interesting results with some TFTs, also the electronic output, so the transfer and the output transfer curve of TFTs. So without further ado, the idea is very simple of this platform, this technology is starting from a single layer electronics, moving towards a double layer electronics, more complex, aiming for a multi-layer electronics. Starting from the very first one, I decided to use and take advantage of polyester carton fabric provided by Sephar company, and this fabric specifically was used as an air filter. Please keep it in mind. I will talk about it later in a moment. As you can see, the lattice of the fabric is very broad, so pretty challenging for us to fabricate a continuous and smooth thin layer on top of this fabric. So what I've done, basically, I cut it down into a 70 by 70 millimeter square the fabric I mentioned before. I placed it into high vacuum condition in the dispatching tool. Before it, I tape it with a vinyl tape mask in order to both have a better adhesion between the fabric itself and finally avoid any sort of shadow effect on the very edge. But also I wanted to be more free, speaking about customization of the mask itself. I've deposited 300 nanometer of copper, and this was the final result. Unfortunately, guess what? The device wasn't conductive at all, because as you might guess, and having a look at this picture over here, pulling very gently the fiber from one on top of the other, we can see a self-shadowing effect between the single fibers, and is also justified by this schematic over here. So if you think about it, we would like to achieve 300 nanometer thick thin layer in a 80 micrometer substrate. How to do that? Well, how to sort this issue out? One idea is to also perform the same coating technique, but on the back, trying to achieve conductivity and continuity between the top and the bottom. And it worked pretty fine. So we tested under temperature characterization for 3 cycles from 20 up to 6 degrees instead of 10 degrees Celsius. It shows some reliability, although not precision and accuracy. To avoid any sort of non-linearity and hysteresis effect, I've calibrated the sensor from the last cycle. So after 3 cycles, I've collected mean and standard deviation from each step. And I was also able to extract the fitting coefficient of the fitting curve of the measured point. As you can see, the temperature coefficient of resistance, or TCR, is comparable with literature with the same thickness of copper layer deposited. Another interesting thing nowadays I mentioned is to understand the mechanical behavior of this device and the capability of them to withstand bending radius. So considering that generally speaking, adult wrist measurement is about 17, 16 millimeter bending radius. For this specific device, we decided to measure it under 3 different bending conditions. So starting from the flat condition down to the 27 millimeter bending radius bend. And as you can see, the resistance increases. So the yellow line here, over here. And of course, afterwards, it was pretty functional, still pretty functional. After that, another very interesting property we wanted to investigate, and as I mentioned before, is the capability of the textile itself to feel breathable, no matter the electronic deposited on top of that. In order to understand this, I would like to introduce you a little bit briefly the water vapor transmission rate and how to measure it. The idea is pretty simple. We have to place a glass full of water with on top the device we fabricate, leaving a tiny window to let the water vapor pass through the device itself on top of it. And here it's sealed. It is to weight the whole system before and after have been left it into a climate chamber at 32 degrees Celsius for an overnight stay. Based on the calculated amount of water evaporate, throughout the sensor itself, we are actually able to determine the water vapor transmission rate parameter. And as you can see, having comparing the device we fabricate, we were actually able to achieve to outscore the majority of the breathable fabric on the market. Of course, it's a matter of the fabric density of the textile itself, but also it's more breathable compared to the average other breathable e-textile found on the market, and also it's way more breathable than the human skin, meaning that the breathability parameter is still preserved. Taking advantage of that, we said, okay, we were able to develop a very nice temperature device, breathable, of course. So what about placing it onto a 3-bottleneck beaker? So on the first one, we placed our device. In the second one, we were monitoring the temperature inside the chamber with an Arduino-based temperature detector. And the first one, and the third one, sorry, we were throughout. So we were blowing air into it. And what we wanted to see, such a thing. So while the temperature increases, as you can see on the right-hand side, we were detected from the Arduino temperature sensor, we were actually able to see the water vapors through the device itself, and in resistance is detected, meaning that we're also able to see the change in temperature of the device itself. To a double layer electronics, I would like to recall the problem I previously mentioned. So the idea, of course, since we are not able to achieve a continuous layer of thin film electronics on top of such a wave and rough surface, another possibility is to implement a planarization layer on top of it, meaning that we would like to smoothen and create an even surface on top of which it's possible to fabricate thin film electronics. So basically, we start from this device over here, in which basically we were able to coat just the yarns with, as previously mentioned, copper, thin film copper. This. So a layer in between, a planarization layer in between the very substrate, the textile substrate, and the electronics on top of it. Eventually, as you can guess now, the idea is to open this hole over here in order to restore the breathability. But this is a topic I'm going to discuss a little bit later. In order to do that, I've decided to mainly focus on two approaches. The first one is a nettle gelatin coated fabric, and the second one is a peak PVA coated fabric. The first one, the idea is pretty simple. I took advantage of a nettle-based fabric provided by an Italian company called Maeco. I've coated it into a gelatin glycerol solution and left it for drying an overnight. And after that, I placed it into vacuum condition, coated with the same vinyl tape mask I mentioned before, and deposited 300 nanometer of zinc layer. And this is the final result. Was it working? Yes, it was working. So we tested it under temperature condition, same condition, slightly the same condition as before, so from 25 up to 60 degrees Celsius. 5-step in temperature, and we were actually able to calibrate it. So as you can see over here, there was a slope a drift slope in the output. I'm gonna mention it and justify that a little bit later. But for now, the idea, since it was a constant slope, was basically to subtract the slope from the very output and achieve a more stable, after mathematical calculus, stable output in the end. As mentioned before, for the previous device, it's very much important to understand the mechanical characterization of this device and the possibility to withstand mechanical bending. So what we have done, we decided to go for a more harsh characterization, so down to a bending radius of 2 millimeters for 1,000 cycles. So as you can see here, measuring the factory resistance in the flat condition, the resistance is increasing over time, but actually was still conductive after the 1,000 bending cycle. To the previous issue we encountered, as you can see here, monitoring the resistance of the device over time, we were actually able to see the device fading away. So within 10 days, the device was completely transparent, and a loss of content was encountered. The main question is it a matter of a formation of a zinc oxide layer due to the oxidation of zinc exposing air, or it's a matter of the absorption of by gelatin of the zinc layer itself? To find an answer to this question, we actually developed this test. So we fabricate the same device on a metal based fabric, the same as before, and in the same fabrication process, the same device but on a glass slide, as you can see here. And also we use as a control the same metal-based fabric with the same thing but with a square in order to have a reference in terms of type. So after 6 and most importantly 9 days, the device was completely gone with a very high resistance in the megohms range. And within 21 days, the resistance wasn't anymore. We encountered a loss of content basically. Despite that, the zinc deposited on the glass slide remained constant, meaning that of course there was a formation of the zinc layer, but wasn't enough to make it completely transparent and to encounter loss of content. The conclusion, of course, is that the gelatin itself started to absorb the zinc on top of it. We were actually able to see a fully recyclable device as we wanted, a transient device. So within 10 days, we have the device completely absorbed by the gelatin itself, keeping it trapped into and sealed into the very substrate, meaning that we are able to perform a DI water-based recyclable process, dipping the fully device onto it, and within 24 days, we are actually able to reuse the whole platform itself for a second round of electronic deposition. Coming to the second investigation I carried out, the PEEK PVA coated fabric. The idea in this case is to take advantage of a PVA coating on top of the same PEEK fabric I've presented earlier with the RTD in order to develop thermistors. So basically in this work, the idea is to add an extra layer, semiconductor, on top of it. How to do that? Well, first thing first, we wanted to understand the relative absorption rate of the fabric itself, aiming for no waste of PVA on top of the fabric itself, dipping for different coating time, the PEEK PVA, fabric onto the PVA solution from 1, 3, 5, 10, and half an hour minutes time. Then after that, we wanted to investigate again the water vapor transmission rate compared to the pristine fabric and see how it actually the coating layer actually affects the breathability of the fabric itself. And last but not least, understand the stiffness, the bending stiffness of the fabric, and how the coating layer affects it. As you can see, there's a pretty clear trend. So the higher the amount of time we are dipping the PEEK fabric into the PVA solution, the higher the material absorbed, but of course the breathability decreases as well, and the bending stiffness becomes greater. So what we have decided is to, for the moment, keep it simple and stick to the thinner layer as possible. After that, after the PVA planarization layer, again, we place it into the sputtering machine and we deposited a 100 nanometer thick layer of metal. And after that, again, 50 nanometer IGZO layer between on top of it. We wanted to investigate 3 metals as electrodes, so starting from the less benign one to the more natural-based one, aluminum, silver, and zinc, in that order. And as I mentioned, the sputtering technique also helps us to achieve the one of the tasks I mentioned before. As you might remember from before, the planarization layer goes everywhere, coating pretty much the entire surface of the fabric, and also enclosing these very holes in the lattice, avoiding to the textile to be breathable, to still be breathable. How to actually go back to the pristine, or try to achieve at least the same breathability as before? Well, the vacuum condition and the string technique, since it's a physical bombardment of atoms and molecules onto the very fabrics, might help. And actually, we saw that on all of the three devices. As you can see, the breathability decreases comparing the bare fabric to the coated one, but also we were able to restore, or at least aiming to restore, the same breathability condition throughout the sputtering technique. Of course, it worked pretty well. We tested all of the three mentioned devices under temperature condition. For the aluminum one, I have to say it worked, but it wasn't reliable. It was reliable, not precise, nor accurate, because as you can see here, it's not achieving the exactly same temperature step as before, and this, of course, affected the calibration of the device itself. To the zinc oxide, unfortunately, we encountered a loss of contacts during the second cycle for the majority of them, but we can actually still calibrate the sensor throughout the first temperature cycle. Last but not least, the silver one was the best within the others, achieving pretty much the same resistance output for all of them with a better precision and accuracy. It also reflects in the calibration procedure. Here, as you can see, the standard deviation is higher compared to the other. I'm going to show you in a moment. For the zinc oxide, the situation was, of course, affected by the loss of contact. And last but not least, the silver one was more stable, precise, and accurate compared to the aluminum one, as mentioned before. After that, we tested it under mechanical condition, mechanical bending, dynamic one, while measuring the resistance while bent completely in bend condition and in flat condition. As you can see here, the aim was to achieve 1,000 cycle, but unfortunately for both the aluminum and the zinc, around 300 cycles, we encountered a loss of contact. We do believe the main cause behind it is the formation of native oxide, both for aluminum and zinc oxide. This native oxide is a very brittle layer, and of course might have played an important role in the mechanical characterization. The silver one, although we were able actually to achieve a pretty stable device in bent and flat condition, being able to remeasure actually the same device after the mechanical characterization. And this was it. So again, in temperature condition, we recalibrated in actually lower sensitivity, mainly we believe due to some mechanical stress of the textile itself, with a general decay of 80%. So coming to a summary of this comparison, we can see the silver-based IGZO thermistor was the best one. What about the recyclability then? Well, since the silver IGZO one was the best within the other, we decided to apply a recyclability method, still in water. So starting from the first device, after 18 days in water, we were actually able to fully dilute in water the PVA and IGZO layer, fully dissolve them, and we're actually able to refabricate on the same substrate the second generation device, and also recalibrate it. As you can see here, making a comparison between the two calibration of the first generation and the second generation, there's a decay in performance. We believe mainly due of, again, some residual stress during the recyclability process onto the very fabric itself. Final, coming to the multi-layer electronics, the idea is to fabricate organic thin film transistors on green fabric. So starting from sustainable fabric made out of hemp, lotus, bamboo, again provided by the Maiko company in Italy, we decided to, with a collaboration of the Max Planck Institute in Stuttgart, we decided to apply the same gelatin glycerol coating technique as mentioned before for the natural-based fabric, and to thermal evaporate 30 nanometer of aluminum on top of it. After that, in order to achieve a dielectric layer, this dielectric layer is composed of two parts. The first one is throughout oxygen plasma exposure, we were able to grow 6 nanometer of aluminum oxide for 30 seconds. And then the second part is 80 nanometer of assembled monolayer. In this very case, it's an octadecylphosphonic phosphonic acid coating and attached to only the aluminum oxide layer. Then, for the organic semiconductor, throughout a thermal sublimation at 60 degrees Celsius, we were able to deposit 30 nanometer of the thienothiophene, which is an organic, a very interesting organic semiconductor, peculiar for its stability in here, and which has shown very interesting mobility at around 3 centimeters square per volt per second. Last but not least, the source and drain contacts were deposited throughout thermal evaporator. So first 0.1 layer of titanium, and then 30 nanometer layer of gold. The final wavelength ratio of the deposited devices is 100 to 30 micrometer, and the overlap is 30 micrometers. Showing some preliminary characterization for the very hemp here, as you can see, we were able to achieve the lowest current within the others, so in the 10 nano amp range. The mobility, although it's let's say comparable with other TFTs fabricate on gelatin, so 0.2 centimeters square per volt per second. The on-off ratio is 30, which is not the greatest compared to the other, and actually we cannot see entirely a very well-defined saturation area for the output characterization here. Coming to the Lotus one, as you can see here, the linear output curve is very much more highlighted with no saturation visible at all, which is also justified by the subtractive swing at very high compared to the others, 490 millivolt per decade. The gate current I would like to highlight is still in the same range as before. Last but not least, so the bamboo one was the best compared to the others, achieving a higher mobility, 0.4, a higher on-off ratio, and a proper saturation area with a subpressure swing of 400 millivolt per decade. So, a conclusion of my today's speech, I would like to sum up everything. So, for the single-layer electronics, for the RTD specifically, we were able to achieve a sensitivity comparable to the literature, a real-time response device, the capability of being bent down to 27 millimeter radius, and breathable electronics in the end. For the double electronics, the first one, the RTD1, again, sensitivity compared to the literature, again, real-time response with dynamic bending to the possibility to withstand dynamic bending down to 2 millimeter bending radius for 1,000 cycles, and a fully recyclable device being able to be absorbed, being able to be absorbed in 7 days in air, and achieving a full degradation in 14 days in the eye water. For the Thermistor one, we were actually able to still achieve a very breathable device. In average, is 1 kilo over meter square per hour of water vapor transmission rate. The sensitivity again is comparable with literature for the same IGZO based one device. The dynamic bending was pretty awesome, I would say, for the silver one, because we were able to withstand a 3 millimeter bending radius for 1,000 cycles, and we were actually able to achieve a second generation fabrication process. For the organic TFTs, I made a spider chart over here to sum up everything. As you can see, the best within the other is the bamboo, which was able to achieve higher mobility, lower subpressure swing, higher on-off voltage ratio, and a voltage ratio of around minus 0.9 volts. Coming to the outlooks of this work, of course, the idea is to still understanding and investigate new cellulose-based fabric, meaning that we would like to create a platform of multiple fabrics made out of different materials, again, lotus, bamboo, hemp, but also seaweed, and so on and so forth. More recyclable planarization layer, of course, we would like to investigate starch as a very interesting planarization layer, and the electric contacts and connection to prove them, of course. The calibration of the sensor and devices has to be improved and is to be considered. Has to focus considering specific purposes, since the original idea was to create a platform which can be shared for multiple application in order to focus mainly on the requirements of the and target perfectly the final application we would like to achieve. The improvement, of course, of the mechanical stability and resilience, not only during mechanical bending stress, but also including washability testing. And last but not least, try to improve for all the new planarization layer, recyclable and nature-based one, the breathability. Last but not least, as reported here in this very nice paper by Van der Velden in 2015, the final aim for this technology as well is to achieve a very nice life cycle assessment and recyclability assessment in general, meaning that we can keep track of all the water consumption, energy consumption, soil consumption, for all the steps of the very fabrication chain we are interested on, starting from the material extraction up to the final disposal. As promised, I would like to leave you with a bunch of further readings that I find very interesting. And before finalizing my speech today, I would like to thank, first thing first, the University of Bolzano, all of these nice guys, supervisors, and that I was able to work with during my PhD, the University of Modena Reggio Emilia, my supervisors, Dr. Giuseppe Cantrella, and of course the Max Planck Institute, Professor Hagen and Dr. Ute Fischenberg. Thank you all for the very nice attention, and if you have any question, please don't hesitate to raise your hand. Thank you.
Thank you, Dr. Albert. Thank you for your great presentation.
Thank you.
Dear participants, now Q&A session is open. You can just speak up or raise your hand, or if you like, you can write on the chat box.
I want to ask one question.
Yes, please. Yes,
This is Gülay. It was a very nice presentation. Thank you.
Thank you so much.
I'm also working on sustainable systems, and by coincidence, the same materials, PEEK and cellulosic materials. But what we do is we are using waste wood to produce cellulose. but you are more concentrated on cellulose fabrics, not the
Yeah.
cellulose, let's say, film. Is it because of the breathability, or is there any other reason? Because I'm not an electronics person, so I may not follow very nicely your presentation. I'm mainly on the material part. And also you are using PEEK as a textile.
Yeah.
And you are coating with PVA. As you know, PEEK is hydrophobic and PVA is hydrophilic. Maybe I missed it, but how did you coat it? Did you use plasma and sputtering, or what was because you cannot easily combine these two combinations.
So yeah, of course, I forgot to mention let's say we let's start from the PEEK PVA. Sorry, since it's the very last one. It's a PEEK based fabric. We do believe, since it wasn't very much hydrophobic entirely, it's a combination of PEEK and some other plastic
Is it
based.
S-PEEK? Could it be S-PEEK? Sulfurated S-PEEK?
Might be. Actually, it's since it's a fabric provided by an external company, and we haven't signed any sort of NDA. They haven't provided us, the entire chemical structure of the PEEK fabric. Another thing just to highlight this thing a little bit more, is that during the thermal characterization, as you might be aware, the PEEK itself can withstand higher temperature compared to the 61.
And dimensional stability also another advantage.
Exactly. The problem, unfortunately, during the thermal characterization process, we encounter some flake delamination of the PEEK fabric itself at around 70 degrees Celsius. We asked the company to provide some more detail about it, but actually they refuse it, and they justify it to saying that it's a proprietary compound we fabricate. It's mainly PEEK, but the further step we are looking for is to have a better collaboration with that in order to understand the actual chemical structure of such a device. To also answer your question, because of the presence of some other compounds in the very PEEK fabric, it was more hydrophilic than the bare PEEK itself. So that's why we're actually able to dip it into water and being able to form this super thin layer on top of the very fabric itself. We do believe they might use some plasma coating themselves, since they also, as I mentioned, they also use it as a filter. So they would like to be slightly hydrophilic, the PEEK itself, in order to filter some water vapor in air, since it's a fuel. It's mainly related to fuel filtering, so you don't want any water dripping into your receiver.
Does it have to be textile form? If I, let's say, provide you film.
So
film, can you?
Sorry. So coming to the previous question, yes, the idea in my very case, is to focus on textile themselves rather than general wearable electronics per se. So the idea is to use this technology in order to fabricate and to embed them potentially in other textiles at the end of the day. So one of the big concerns nowadays for the wearable electronics is that, okay, if we fabricate, for instance, even and smooth and continuous layer made out of, for instance, just gelatin, at the end of the day, we have to attach it to the body, which is somehow not very pleasant, or we should find a way to somehow attach it properly. There's going to be sweat, there's going to be moisture, a lot of other, let's say, character playing a role in this very embedding process. To tackle this issue down, the idea is to rather to come up with a new wearable, let's say, technology per se. We can think reversely and try to embed on the very textile the technology we would like to fabricate. That's the only reason behind my the textile choice.
How repeatable then because depending on the knitting process, the textile may change and the qualities will change.
Absolutely.
Yeah.
But at the end of the day, we are targeting specifically, I haven't mentioned it before, but it's a plain wave. So the most simple one, trying to being able to be reproduced for the majority of them. Of course, it's a matter of eventually speak with the textile companies and collaborate with them in order to make a fine-tuning of the textile itself, so the way it's fabricated, and in order to achieve a smoother layer electronics on top of it. But of course, it's a matter of improving and also the speech with the companies themselves.
Because SPIC is not, you cannot easily dissolve. The recyclable part, if it is directly PIC, it's very difficult to dissolve it. So there should be some modifications for the...
I think, but absolutely, you're right. But the idea is not to dissolve the PIC at the end of the day. So since it's mainly biocompatible, but it's not biodegradable per se, or very easy to dissolve in water, as you correctly mentioned, the idea is to keep the PIC itself and to reuse it for the second generation of...
yeah, that's right.
On the other way around, the nettle-based fabric, for instance, one of the collaboration I had was with an agronomist who was very much interested to fabricate a device for measurement the growth of an apple fruit. And after that, he wanted to dispose it into the orchard itself. And in this very case, for instance, the nettle-based fabric can well modified in order to being able to follow the actual mechanical deformation of the apple while it's growing, can be easily disposed in nature, for instance, if it's only nettle, of course.
Yeah, it's a good idea.
Thanks.
Thank you.
Thank you so much.
I will contact you.
Thank you. Absolutely, please.
Yeah.
Please do it.
Any questions?
I may ask one more question.
Okay,
absolutely.
You are using biopolymers like gelatin or PVA for coating.
Yeah.
And when you look at the washability results, these are very easily can be removed from the fabric.
Yes.
How many times washability are you testing for those kind of electronics?
Thank you so much. It's a very interesting question. Unfortunately, for now, we haven't tested the washability yet of this device because, of course, the main focus was the recyclability for now. The idea is to finally encapsulate them with an easy to remove encapsulating layer, let's say, on top of them. The challenge here, of course, is to keep the same breathability parameter at the end of the day, but with encapsulating properly the device itself.
One more question. For the PVA, do you have any molecular weight concern? for the coatings? Does it have to be at certain molecular weight levels?
No. Yeah, now on top of my head, I cannot remember the molecular weight, sorry. But yeah, you can easily find on, it was one of the most
Well,
common
mechanical
one,
properties change a lot.
Yeah, absolutely. I can share the molecular weight with you later on.
Okay.
I forgot to mention it, sorry.
Okay, that's okay. Thank you.
Thanks. I think we have a...
Nokta Hanım, benim şeyimi siz mi kapattınız?
Hayır hocam.
yeah. It's not sensitive to sweat. Well, of course, it's gonna be sensitive to sweat as well, since it's not encapsulated. So it's the same concern as before. For the moment, we are just focusing on the possibility to measure temperature. I never said it's gonna be embedded into human body. So, although the temperature range we tested it's human body based one. For the moment, we are just aiming to create a general platform. Of course, if it's a matter of sweat based, we have to encapsulate a little bit. We have to encapsulate it to withstand both the sweat but also the washability condition. That's entirely true.
Can I ask one more question? Did you use textile itself, different types of textile for the electronics applications? The cellulosic one.
You mean if I made a comparison between
the commercial cellulose textile?
Yes, we bought them from, well, we purchased them from an Italian company called Maeco. They are in charge of the whole production chain of their textile. They're mainly focused on cellulose-based textile. So they provide us both the hemp, nettle, bamboo, and lotus, the one I showcased before. So yes, that was also the idea. Try to find something really present on the market and take advantage of that for the very first step of the work.
Thank you.
Thank you.
Thank you, Dr. Albert, for your presentation and your answer for questions. If you don't any question, time is up. Thank you all participants for your participations.
Thank you, Nokta. Thank you all for the kind attention, and yeah, was a pleasure.
Thank you.
Thank you.